Evening, everyone. This is the data building pipeline of Overwatch Talk. My name is David Clyde. I'm a senior software engineer on the Overwatch team at Blizzard Entertainment. I have a lot to get through today, so there's no slides about Overwatch or myself. You're already here, so presumably you're okay with at least one of those. When we set out to make Overwatch, we set a bunch of goals that we wanted for our content pipeline. These goals were what we felt would best let us iterate as quickly as possible to help us achieve that Blizzard polish that we rely on so much. We're not going to touch all of these particular goals, but there's definitely some ones that stand out. The ability to share content with others, to test out our changes without having to commit them, allow us to iterate a lot quickly. But then the most important one for us is this ability to pull a brand new build and latest content, regardless of what state you were in before, within 5 minutes. We didn't want people coming in and pulling one build in the morning, and that's all they have for the whole day. We generate something like 30 builds per day throughout the day. To accomplish this, we didn't go with a lot of the standard asset storage mechanics that a lot of teams use. We decided to use SQL and HTTP. SQL, we use Oracle as our global SQL servers. We have a lot of Oracle experience at Blizzard, and we felt that this would be a good choice for leveraging our expertise that we had. And HTTP is a standard way to transfer files. Both of these technologies are used worldwide for very large-scale problems. There's a lot of technologies that revolve around helping them scale, so we knew that regardless of what size the Overwatch team happened to be, whether we needed to be able to access content from another continent for the local team or whatever the case may be, that we would be able to scale this. It's also relatively easy to find some IT experience that knows how to work with these. There's programs for finding, like DBAs, that kind of thing. So we knew that even though we were making a custom setup, we would be able to find people to help us support it. These are our global asset services. So we've got hard disks in brown for our global file store. The yellow there is an HTTP server. The blue are different asset schemas that we have, and orange is a custom server that we wrote called Asset Repository. Being Blizzard Entertainment, all of our games are online. We also have a lot of server experience, so you're going to see us leveraging that as we build this pipeline. First, we're going to start on these, the asset schemas. One of the things to call out here is notice there's a global schema, and then there's like a 1.0 and a 1.1. We wanted branching to be built in from the ground up for our content pipeline. We knew that we'd commonly be working on features well advanced of what we're about to release, and we actively work in 3 to 4 content branches at any given time based on what features are coming along and how far along things are. These two asset schemas, so we have 2 setups. We have the global one. This contains all of our metadata. It's got your user IDs, the workspaces, which machines those users work on, a list of all of our branches, our codes in Perforce, so we know which Perforce repository matches with which content branch, commits, which is essentially like a tracking for change lists. And that's kind of where we set up our architecture. That's source control. Then the other one is a branch-specific database. This is your 1.0, your 1.1. These have 2 tables only. There's one table that is just a asset row for every asset in the game. That is your head snapshot of what that branch looks like. And then there's another table that has the history for every single one of those assets going back, indexed by both the ID of the asset and the commit ID. We use that guy for history queries and more expensive queries that we don't run nearly as often. You'll see there a very small schema. I don't know how easy it is to read, but the goal here was to keep everything really simple. This setup actually knows very little about what our assets look like. They don't care. They just want to be able to identify them and let you query them, and that's it. As such, our server is also very simple. Let's go into that row a little bit. This is what our asset looks like at the global service level. We've got a GUID. That's a unique identifier within our project, not really listening to what that G stands for. And it's actually, for us, this is a 64-bit ID. It's not like a UUID you might see otherwise. We encode the type into the first 2 bytes, and then the rest of the bytes are available for the unique ID of the asset. We've got the commit ID when it was committed. We've got flags, whether it's been deleted or archived, etc. Nothing truly gets deleted, so we've got those flags there. And then we have a binary payload, and this binary payload is just whatever we need to define this asset. But we restrict it to 64K. We do allow that data to be compressed. Again, it doesn't actually care what's in there. But we've got up to 64K compressed. We've got the name. If you need a separate file, either because you don't use the same format that we do for assets, so maybe you're a Maya file, etc., or just you're not going to fit in 64K, we have this optional SHA-1, which is a reference to a separate file that we're going to put in our file store later. And the last part is the remaining binary blob is structured data. Structured data is a custom-made binary tag format that we have and that we've developed internally on our own. We use a structured definition language that kind of looks like that on the right side of the screen to specify what we want our structs to contain, what fields they have, etc. This is the guide that defines what an asset actually looks like. We auto-generate code based on this, so we can generate our serialization and our data conversion. We actually use structured data at runtime as well, and we just have a converter that goes between the editor format to the non-editor format so that we can use it for runtime. I mentioned that SHA-1, that's referencing files, so we're going to go into our file store. Our file store is content addressable, and that means that we actually store the files by their hash. So the file name is actually the SHA-1 itself. We're going to notice a lot of IDs and hashes throughout this talk. Everything kind of uses this union of the ID, the name, and the hash, and we use that concept a lot. We do bucket the folders by the last 2 bytes. That's just kind of like make sure we don't have too many files in the same folders. To kind of highlight how much iteration we enable people to do locally and how non-dependent we are on our global services, we currently have 1.7 terabytes in unique history of all of our source data, the files, and 900 gigabytes of that is the current head snapshot. So that's not a lot of iteration. On average, our files have only had 1 unique change to them, but of course, some more than others. This runs on a Linux machine running CentOS. We use Nginx as a HTTP support that we use, and we added a custom Python validator to it. One of the most important things about this file store is that it's 100% reliable. No 2 people are going to collide writing files. Luckily, the file names are SHA-1 hash, so we know if 2 people go to collide that it's going to be the same content, so whoever's first wins. Reliability is very important. So we actually validate that the content uploaded matches that SHA-1, which is in the file path anyways. We run 64 gigabytes of RAM. We don't do anything fancy for caching. We just use the standard operating system's file cache to accommodate that. 64 gigabytes for us is just how much that fits our current daily working set. Really, how much RAM is just matters what's your daily working set. You want to make sure it can contain that and then a little bit more. And like I say, hardware specs can vary for team and their needs. So now we're going to leverage some of that server experience at Blizzard. We're going to talk about asset repository. This guy does anything you can only truly do at the global level. He creates all base GUIDs, so any unique new IDs that you need for assets. He manages exclusive checkouts. All of our content, only 1 person can have it checked out at a time, even across our various branches. He handles commits. For the most part, that's just writing records to the database, but it also means that it goes and handles any downstream branch updates. So the moment you commit an asset, it is now actively in every downstream branch the very moment that you commit it. We don't have to do integrations after the fact. And then if you want history queries, you go to him. So we have a bunch of local asset services. You'll notice these mirror very closely the global asset services. Everything here looks very similar. Everything on the left side of the screen is our global services that are on a server somewhere you communicate with. And on the right side, this runs on your local machine. We're going to talk about this local workflow server. This guy is responsible for caching a head state. If you sync assets, you have a snapshot of what assets looked like at that time on your local machine. You're going to have these for editing. This is where we get them for building. This is just he stores stuff there. The table here is a little bit more complicated. That's just because we extract some of the information out of that payload for quick indexing and queries. We have a name cache in case you need to search assets by name, stuff like that. One of the most important things about this local workflow server, though, is that abstraction between local services and global services. If you want to do a history query, you talk to him. If you want to check out an asset, you talk to him. He's going to redirect some of that work, but no matter what, you have a local server to talk to. If the global server goes down for some reason, if we have a network interruption, you can continue working. You're just told if certain operations can't be done. But you can do a local checkout if that's not working, and you can continue editing and working. You just can't commit your work if those services go down. And then your local file store is what we're going to talk about next, but there's not really a whole lot to this. The global HTTP server is literally just an HTTP server sitting in front of a bunch of folders and files. That's exactly what it is locally. We store them the same way with SHA-1s. We use a very simple, it's just a .NET, like C# asset server running standard HTTP server code provided by the .NET libraries. But he again handles redirection. So if there's files that you go to fetch and they're not on your local disk, he's just going to redirect you to that global HTTP server. The goal is you just have one set of services to talk to. They're local, so they're always there. And then just whenever they can't accomplish the needs, they'll go to the global server. So now we actually want to compile our assets. Now that we've got all of our assets, and that pipeline as it's set up is very core to how we build our content as well. And you'll notice that, again, all of these services look very similar to what we had before. There's a global file store with a global HTTP server, a global custom server we've made, and a database behind it. And then locally, we have a lot of the same things. Looking at everything together, we have this. And you can very clearly see how everything mirrors both horizontally and vertically. We're using the same technologies to solve what is essentially the same problems. And we're doing it in a way that scales extremely well. The only difference is that this, on the right-hand side, those two HTTP servers, we don't actually run two different HTTP servers. We just have that one server, and based on the URI passed to it, it logically decides which file store it's going to write into. So now it's time to actually build our data. So we're going to talk about this cluster here, and this is what we call data build. Data build is our executable that goes from type to type and compiles them in order, making sure that everything is built that needs to be built. We run in a everything is constantly built state. We don't build things on demand. We only build certain things or certain maps. Every map is there. All content is available to the user. One of the things that's really important to us is knowledge of how everything depends on each other. So the first thing it actually does when it processes an asset is extracts that asset's references to other assets. And this is really easy for us because we're using that structured data. And structured data has a very specific format to it where we can actually opaquely parse an asset without knowing what type of asset it is and what its structure is to extract all of its references to other assets. And those aren't names or anything like that. They're the GUIDs we talked about earlier, so they're not going to change, and we can just parse those out and store those in our local database. So we have two different schemas for data build. We have a branch-specific one. This stores what your assets look like when they're compiled, just records. They've got things like the GUID, the MD5, and the size for every asset that's compiled. And that represents your state of what the game currently looks like. You only have one copy for an asset. You don't have every copy you've ever compiled there. The branchless one, however, is basically just a mapping of inputs to outputs. So if you change a checkbox and you compile that asset and then you change that checkbox back because you didn't like that change, we've already got that record in this branchless database and we just refetch it. So now we actually want to actually build everything. The first step is we have to have assets. We call this source pull. This is actually a local workflow server operation, but data build's kind of the face to everything. This operation actually takes 10 minutes as we download 1.4 million records and write them to disk, and then also take care of all the extraction I mentioned. There's those extra rows that we take out of the payload, stuff like that. I haven't mentioned this yet, but we use SQLite as your local on-disk database, and the result is that SQLite uses a singular file setup. So when you're not using it, there's one file. So for us, that file ends up being 600 megabytes for that local workflow server state of your assets. I don't know anyone that's good at math, but 10 minutes is already higher than our 5-minute mark that we're aiming for. So we'll go into that once we accumulate all the various problems that we have. So now we're building for different target platforms and different environments. This is what our expectations are, who's going to consume the data. Overwatch is on PC, Xbox One, and PlayStation 4. So we've got 3 different target platforms. Technically, the server is a 4th platform. We actually compile some of our data different for the server as well. So we actually have 4 different environment platforms we're going for. Environments is this concept where it's another dimension to this. So we have dev content and external content, or shipping, and that if you're going to make a list of all the heroes, for instance, our list of heroes may be different than the list of heroes we want you to see. So we do have some things that build things differently depending on which environment they're building for. So each builder, to accommodate this, returns a compiler ID. This compiler ID could be something as simple as just the code version. The first time you wrote the code, it's 1. You make some changes, it's 2. It represents the logical code that's going to actually build your content. If you do want to branch your behavior for different platforms or environments, you can take those enums and hash them into your compiler ID. If you return a different value for PC as you do for the server, then we're going to call you once for both compiler IDs. So you're going to get called twice in that scenario. If you do something custom for both the environments and the target platforms, that same asset can be called through that builder up to the number of combinations that we have here. Depending on how many assets use that, that can scale very large, the number of assets that we have to compile. Similarly, we have different sources. So one of our original goals was to be able to specialize content separately for languages as we do for regions or platforms. Turns out platforms don't like it if you call their controller buttons the same as another platform. So you want to be able to change that string so that on the Xbox, the right trigger, and on PS4, the right bumper, whatever the terminology is, you're allowed to customize that. And for regions, some regions don't like different content, so we can customize that there. And then obviously the one that most people are familiar with, the localization. This can escalate largely, but we end up storing the combinations of what you do or do not support into what we call the localization ID. And this represents the input content. 6 of our types use region specialization, 13 use platform, and 16 use locale. So again, this can start escalating a lot. We support 13 different languages. For anything that supports locale customization, it means that we have to build that table potentially up to 13 times. Now we're going to actually build. Structured Data Builder, because structured data is this generated code platform, is very simple, and it handles 80% of all of our asset types. We can just do that standard conversion from the editor format to the runtime format, and everything's handled. Similarly, you may have to just calculate some specific value. You may want to figure out, just do some custom logic at build time using the accumulation of editor data to make your runtime data. And so the other 15% are just derived custom versions of that structured data builder. And the last 5% is kind of where the engine team goes in, and they're going to make what the model format and the map format, and they do all the crazy. We use all the dependencies in the entire world to build all of our pathing data and reference every model and that kind of stuff. So across 203 different types, we build 170 and process 180. Processing, again, the difference there is if we're just extracting references, and that helps us get to other assets. Those results, once we build them, are stored in the compiled file store, and then the database record is written both to your current state and so the branch database, and to your branchless database, just for a record for later. So these are what the outputs look like. So when we compile an asset, this is what the output looks like. Any given asset can actually generate multiple compiled assets. So we redundantly have the source GUID and the compiled GUID, and then the information you'd expect, like the MD5, the size, some flags, that kind of thing. However, one of the more important fields is this compiler hash. This is everything it went into building this particular asset logically. So we can bucket or namespace our assets within our database this way. So if I want to get all the assets of a particular type with my current code version, this is the ID I would use. And we simply take these various inputs, we hash them together, and we go about our way. The source hash, however, is arguably the most important value we have. Because we have an asset, let's say a model, and we know it references a material, and we know that material references textures, and for some reason we need all of those assets to build our model, then we can recursively go through every single reference, fetch them. We do filter this based on what we declare are actually dependencies. And we can get a list of just headers. These are the assets, they have the asset ID, they have the hash of that payload, they have the SHA-1 hash if it has a file, and we've done very little just using database queries to get the full list of every asset we're going to need to build this content. And we can hash that right there. This is a very small structure to hash, and so if you have 16 dependencies, we hash that structure 16 or times 16 in size, and we generate a unique ID that represents your input content. So we'll know if we take your compiler ID and this source hash and we build that combination of content, that it's going to always result in the same MD5 no matter what. That has to be a rule, everything has to be deterministic. It also means if we build two different assets that are physically identical, they'll end up having the same source hash and we actually don't have to build them a second time. The end result is a manifest. This is just a combination of the GUID, the size, and the MD5 for every compiled asset that we have. There's one manifest per configuration, so on PlayStation, in French, on the US region, etc. And then we simply go through, and for that current configuration, it has the compiler ID that the builder told us was its current version. We will fetch all the assets out of the database, create a giant manifest of what your current state in the game is, and that's every asset that you need. During this phase, we also build what we call packages and bundles. These are processes that need to know about your entire asset state. They're kind of holistic things. Packages are like mini manifest for concepts like heroes or maps. So now that we've got all that, we've actually gone through and built. We're building for a dev build, which is just two configurations, Windows and server, dev setups, no specific locales, etc. We've got 350,000 assets. We've made it so easy to make assets that they make assets out of just IDs. We've got bone labels, which are literally just a GUID. So we have to go through and build 350,000 assets and two configurations. This currently takes 12 hours on an 8-core machine. So again, way beyond our 5-minute mark. Full retail is quite a bit worse. We've got 3 million unique specializations across the different locales and regions and that kind of thing. 65 configurations in the end, and I've never actually compiled this on an 8-core machine to see how long this takes. I don't take enjoyment in waiting long periods of time. So one of the very simplest things we can do is just get access to more cores. 8's not really sufficient. Our material table alone has over 10,000 different materials, and they actually generate shaders. They generate over 22,000 shaders, some of which, not all, can take up to 5 seconds to compile each. So that's not really going to cut it. We're going to need to distribute this. We use a distributed build system provided by an SDK that we use, but for the most part, it's really easy for us to hook into one of these because all we need to do is take the dependencies we've already fetched, serialize them to disk, and then use that as the payload of what needs to be built. The distributed build system takes care of sending that file to the different machines. There's different solutions out there. It really doesn't matter which one it is. But for any of the large files, we actually haven't loaded any of the large files. The distributed agent can connect to our HTTP server, and it will fetch the files that either we've edited and made locally or redirect you to the global file store for fetching the content necessary to build those assets. This actually gets us down to about 4 hours. We have a lot of types that are I/O bound, and it doesn't actually make sense to serialize them to disk, transfer them across the network, load them back up, make results, transfer it back, etc. So we only do this for some types, anything computationally expensive. So what do we have now? We have a 10-minute pull. We've got 900 gigabytes of asset file data, 1 gigabytes of executables as part of our build, 8 gigabytes of compiled asset data as a result, and 4 hours of data building time. So in order to do this in 5 minutes, our goal is to just not do anything that we don't have to do. So pulling a build, we don't actually pull the whole build. Even though there's a whole gigabyte of executables, we only pull about 150 megs. The build is broken up into various buckets. We've got servers, we've got tools, we've got the client, we've got manifest, 65 configurations. You don't really care about any of that. You're going to pull down the tools, and that's it. And if you want to use local data, you then activate that build with data build. It builds your manifest, which is a version of what you currently have content of with local changes and everything. Seed databases. So that 10-minute pull, it's actually only like 15 seconds if you've pulled before. If you've pulled down all the assets before and you're only pulling down the changes over the last day, 5 days, whatever, that takes about 15 seconds. So what we do is every morning we do this for you. So we spend that 10 minutes downloading absolutely everything. We put together the singular 600 megabyte file, and if you don't have a database to pull incrementally from, you just download that from the server for your current branch. So we've just turned 10 minutes to about 30 seconds. The next is incremental building. Obviously, it makes sense that you shouldn't have to build something you've built before. This is a concept that we hammered on at the very beginning. Everything's ID-based and hash-based. We end up with the MD5s of the compiled assets. It's actually very easy for us to ensure that we're always building all the data 100% reliably. The very first test we made was one that built everything from scratch and one that built everything incrementally and compared that resulting manifest. This needed to be 100% reliable. We don't do nightly builds where we build all the content. Even our build machines, everything is doing incremental building it all the time. Except for the test that makes sure we don't break this, everything is incremental. So this highly relies on that source hash that we mentioned earlier. Because we know exactly all of our dependencies, the builder actually doesn't fetch any of the data itself. We fetch them all ahead of time to ensure that our dependencies are 100% accurate. We don't let them fetch additional assets. So that we know at all times, we know exactly what it takes to make an asset. That hash is 100% accurate. And this is multi-tiered. So first we check the table for the branch to see if it's already been built. If it's not there, we're going to go to that branchless database, the one where maybe you had built this asset in a previous branch, or maybe you had toggled your changes, so it's been in there. So that's just, we go to that guy. And then also on top of that, we do a hash at the table level. So if we know that table's been built, we're not even going to visit that. Some types don't change very often, and so we're not even going to visit the table to do incremental checks on the assets if we know that guy's built. So now we have this other thing we haven't talked about, and this is just the global file repository for compiled assets. Again, he's got a very similar setup to everybody else, and basically, he's just a way of storing our version of that branchless database. That branchless database is very useful. It saves us a ton of time, so it'd be really nice if I could benefit from your changes and you could benefit from what I've compiled. So we have a compiled asset repository. It's got a global asset schema that is almost identical to our branchless schema. Because there's 13 different languages and I only build one language, but the build machine builds 13, we do bucket the changes based on locale so that I don't pull down 13 languages worth of data to make that as fast as possible. I also once maybe exploded the length of an array on a 32-bit thing by pulling down all languages. So we decided to bucket it that day. So that leads to compiled pull, and this is simply a way for us to download all the records that other people have already compiled. Pulled down the last 30 days. We have a system in place for basically touching assets to make sure that the compiled thing that we're still using has an up-to-date timestamp. So we just make sure that we download anything that's changed, and we even globally, we only store the last 60 days of relevant content. We didn't used to do this. We left all compiled assets ever up there, and we had grown to about 19 terabytes of data. After we cleaned it up to only the last 60 days of relevant data, plus reserve builds, anything we've put out, we want to keep those, just in case we go back, we don't have to want to wait 4 hours to test out the build. So right now, that's 25 million files across 1.6 terabytes and revision history generated throughout 60 days. This is actually, again, this pull is incremental, but on top of that, we do it asynchronously as we download the build, or as we build the data. So while I'm building our first asset type, I'm still downloading the list for the compiled asset type. We can't do this with the source data, because the source data has to all be together in one transaction. But with the compiled asset data, we don't care if we got a couple additional assets that we hadn't gotten from the previous table that we're a little bit ahead on time. We're okay with that. So because of that, we're always pulling the next table while we're building a table, and this guy's cost is almost entirely hidden except for that first table. So at this point, now we're getting the list of compiled assets, and we can look up based on our source hash whether or not what we have locally matches what we pulled down. And we can do these all with very fast SQL queries. We haven't actually built anything in the ideal case. At most, you're usually compiling things that you had changed locally. So whatever you had changed, if you hadn't compiled them for some reason, you're compiling those and that's it. And this has a lot of benefits. You're not pulling down any of those 900 gigabytes in source files necessary to build our assets. You're not pulling down even the compiled asset itself. So if we make a map and that's 100 megabytes, you don't even have to download those. You just downloaded the asset record that told you the MD5, it told you the file size, and it told you the GUID. You don't have to worry about any of that stuff. And in the end, what you end up with is just this manifest of records that you have. That's every asset in the game. You can visit any map. You can go to load up any hero. It doesn't matter if it's an official map. You technically now have a manifest that knows about every single asset that we have in the game. So where are we at now? We've actually hit our 5 minutes. So we talked about the pulling down the 150 megabytes. I'm probably being generous with saying that's 30 seconds. Obviously, that can depend on your network and stuff like that. We've got a 2-second to 30-second asset pull. So either you have to download that 600 megabyte file that we generated on the server for you and then do an incremental, or you're just doing an incremental. Either way, this is either very quick or up to around 30 seconds. And then we've got the compiled asset pull. So that's really about 30 to 60 seconds, but that's hidden behind the scenes. Like I said, other than that first table, that's off running on another thread, and we don't have to wait for it. On average, our builder only has to wait 1 to 2 seconds at any given time. Or total, 1 to 2 seconds waiting for that guy on average. And then we do 2 to 3 minutes of hashing our content. So 130,000 assets, and then doing queries for hashing every dependency and getting the list of all the various things that we need to calculate that source hash. It turns out CPUs are actually really, really good at taking data and just crunching numbers on it. So this doesn't take a whole lot of time to go through every single asset we have and to do this. This is 2 to 3 minutes, and typically does include any changes that you have locally if we have to build those. Commonly, we built them as you made the changes, so even those we don't really have to change. But if someone did up a compiler ID for what you had changed, you will have to recompile those. So unless you have 400 textures changed and we up the texture version, which we don't do very often, you're not going to spend a lot of time doing this. And then it actually takes us 1 minute to build the manifest and the packages. Most of the times in the packages, having a concept of every reference a hero has, et cetera, or a map can take some time. We have to load every asset, every reference in the game. We actually store compiled asset references separately from source asset references because they can differ. So we use that to kind of build up what every package has. So now we're going to load things in the client. And we don't actually have anything locally. But luckily, we've got this asset server, or this HTTP server sitting right here on your local machine. And not only that, but it will redirect you to the global repository if you don't have the files. So this makes it really easy for us to load up a build, because all you need is the executable. Engine is built from the ground up to handle all loading asynchronously. In retail, we actually don't have any functions that can block and wait for a resource to finish. You can never pause a thread to do that. You either have to pull or handle callbacks, or you can set up some other mechanic for knowing that a concept is loaded. Again, that's kind of where packages come in. You can say, is this package loaded? And you can then turn on whatever feature that may be. We load from an archive container, always. For Blizzard, this is the CASC, which stands for Content Addressable Storage Container. Every game is now on this guy. He's basically a growable container that we can, that's indexed by the MD5 of the file that you're using. So again, it's built in, everything's referenced by hash. So we cache values in there. So if you go to load, you've never had one of these before, we create this CASC container. We download the asset over HTTP. We store him in the container. Next time, you're not going to have to fetch him. Turns out people work for us for more than one build, so they have all the benefits from previous builds or even previous branches. We share this guy across all those various things, and it makes it really easy if he ever gets too big, you've worked on so much content that he's just bloating and you need some hard drive space back, we just delete him and everything gets re-downloaded. In fact, our entire compiled asset state, at any given time, we can delete the entire folder that contains all locally contained files, databases, and everything, and we just pull a new build, and everything's been regenerated. At runtime, this container is accessed by what we call TACT. It handles downloading from CDNs instead of the internal available HTTP servers. He handles auto repair, he validates MD5, stuff like that. This is again used by every team at Blizzard. Internally, like I said, we just use our own HTTP server, and we just download from him, since everyone happens to conveniently be running one. And that brings us to playtest. So now we've built all your data. Your data is different than everyone else's data because you pulled to a specific point in time. You have whatever changes you've been working on, and you want to show other people your stuff. We have a tool called Tools Tray. You right-click on it. You say, I want to create a playtest. You can choose to use your local data. And what it does is it puts together a broadcast message to send to all the other tools trays on the floor. And it tells them, there's a manifest that I just uploaded to the network, and it's for this build, and I'm hosting servers for this. Here's where the servers are. They're on my machine. So anyone else can just go to join a playtest. All they have to do is download that client executable, which is already available as all of our builds are up on the network. They can then download that manifest, which is only about 10 megabytes. And then they just connect to your asset server, your local HTTP server. So any files they don't have, because it's what you've developed on, just naturally gets downloaded from your machine. And if for some reason they had never visited that map before, that just gets redirected to the global file store instead. So your machine's not actually getting hammered with a lot of I/O, at least not anymore. We had a couple complaints about that, so we got that fixed up. So now you can make any changes you want. Say, hey guys, I just put a playtest up, please come and join it. And this is actually something we do on a very regular basis. At any given time, you can look at the list of all playtests, and we've got about 15 of these things running as designers and QA, and everyone's using different builds. If someone has a bug and we've never seen it before, depending on the nature of the bug, I can actually go jump in their playtest and see what's happening. And if it's data related, we can get that all figured out. So of course, we have some future improvements that we want to do. Right now, we do build absolutely everything. We ensure that everything's in a known compiled state. And that's really nice for pulling down a build. But every time you make a change, we also build absolutely everything. And for that depends on that file. This works out really well for simple pipelines, but we actually have a couple of core effects that get applied to every character in the game and every material that character has. And if you change one of those, it takes like 20 minutes to wait for everything to be built, because if you impact shaders. So one of the things we want to do is switch to a lazy system. It's going to make sure it's all built before you commit your changes, but while you're in the editor, it's going to just invalidate everything, and then everything that's currently loaded will trigger a reload notification and build only those particular assets. This is something we want to do to really maximize the workflows that some of our more difficult pipelines suffer through. Also, building a table at a time is really wasteful. You could be loading more content. You could be building more than one table. If all you're really doing is hashing things and then going, oh, I already built this, we could easily be doing that for a lot of tables at the same time. So we want to switch to a job dependency system. This is actually getting very close to being done. And it eliminates our fork and join. We don't process all the assets and then build all the assets and rejoin to the same thread. So by using a job dependency system, we're going to run a thread where one's for this database I/O, one's for this database I/O. There's 8 for just doing CPU work, and 1 for standard like file loading, 1 for network file loading, that kind of work. And this will eliminate a lot of our waiting for things to finish before we proceed. It will automatically ensure its dependencies are done and continue. We estimate that we can get the 2 to 3 minutes down to 1 to 2 minutes by doing that. And then also single points of failure. I mentioned what happens if the asset repository goes down. We handle that very gracefully, but it'd be really nice, since it's actually dumb, really dumb. It doesn't have any states, anything like that. You could actually run it on a local machine if you wanted to, as long as you forced your client to connect to it. So we want to run a couple of different services. We want to make sure that if the standard HTTP front end goes down, that we can connect to a different one, that kind of stuff. I didn't work on all of this myself. I did a lot of the data build work, but all of these fine people did a lot of the other things that we've been talking about. The obligatory lead call out, as much as that's a joke that's obligatory, he actually did a lot of help with providing different ideas and concepts of how we would implement them and how we would do different things. And that's the fastest run I've done of this. So at this point, I do have bonus slides if we want to go over some things, but I'm going to open it up to you guys for any questions and go from there. While people are doing that, please make sure to fill out the forms and stuff like that, or not the forms, the questionnaire to help us choose whether or not I should come back or not. And yeah.
Hi.
Yes.
I was just wondering if you ever ran into any dependencies between code and data, and how you were able to either resolve those or avoid those in the first place.
Sure. So the question is if we've ever run into dependencies between code and data and how we avoid those or resolve those. The answer is yes, all the time. And it's usually people that aren't necessarily taking the time to make things backwards compatible or things like that. The most common one is that structured data language that we have. In order to define a structure, you have to create it in code, and a build has to exist for you to then make it. But if you check in that content, no one can actually make that asset. They don't have that code yet. So depending on the different workflow, we actually will try to encourage people to commit that definition of what that asset will be ahead of time. It doesn't actually have to be functional. You don't have to be using it yet. You just commit it so that people can create it. And then do the work that supports it, then commit it. So depending on what it is, there's different policies. We actually were a little lax on that and just recently made a policy that programmers have to go out of their way to do that, because otherwise you can easily break a content engineer. Even with a build, they can pull latest content. And if they pull something that can't compile, depending on what it is, it can break them. Yes?
Yeah, so I was wondering if you could talk a little bit more about that. So do you have the problem where there's been a change to an STU file checked in, and then there's a content creator that has not synced up to that change of the STU file, then they want to work on some data format that has already got that new version. Does that make sense? So they have a old binary, but they're trying to work on a file that's now been updated to a new version.
We surprisingly don't hit that a whole lot. Commonly, if we're adding things to the structured data files, it's for some feature, and the designers are specifically waiting for that feature to be available before they do that. It is possible, and in fact, it's most likely when we work in upstream branches and there's downstream branches that have changes into those. We don't hit that very often, honestly, but we do try to leave unknown data in the editor format. So if there's a field we're not familiar with, we're going to edit the other fields, and we just leave that particular guy alone and serialize him back out, hoping that we didn't just break things. For the most part, we do support serializing out our structured data to JSON, and we can handle merges manually. Usually we'll bring over a programmer to do that if there's an issue like that, but it actually surprisingly doesn't come up very often.
Yeah, so just so I can repeat that back to make sure I have that right, if your tools are encountering fields in the STU file that they don't know about, they'll just leave them alone. So it's kind of like a property bag, where if there's unknown data, then that wouldn't be modified.
Yes, yeah. Like I mentioned earlier, we can opaquely parse the structured data, so we know there's a float here, there's an int here, there's a string, without actually knowing what it is. So we use stuff like that to do that.
Thanks.
Yes?
Hi. I was wondering if you could comment on how you guys minimize the amount of data you pull down to the clients, like end clients, when you do a patch, and does it relate to this system at all, or what's being built by the system?
Sure. So the question was how we minimize the content that people pull down in patches, like the actual retail clients. The answer is we don't always do a great job, but we actually have a series of tests that take, when we build the game, when we build the manifest, we actually dump out to a database every asset that actually was going in and information about it, and we can compare two different databases from two different builds and get a list of exactly what assets changed. One of the biggest issues we have is that all small files, anything under, I think it's like 2K in size, we actually bundle up into one concept. So like every hero asset under 2K gets bundled up. Because we made it so easy for them to make so many assets, we have a lot of those. And if you change one of those, you've now effectively changed the whole bundle. The answer is that actually impacts us differently on different platforms. So on console, we don't actually have a within a file change strategy. So we actually that whole bundle is now different. On PC, the team that implemented Tact and Cask, they have a system where we submit to them a manifest, and they'll go back up to 5 changes on any individual asset and generate delta patches that you can then apply when going. So if you ever see, I think it's downloading patch indices or something like that in the BattleNet launcher, that's fetching that information.
Thank you.
Yes?
Okay, so this whole caching and the caching of content system basically relies on everything being deterministic all the time, right?
Yes. Sorry, he asked if we rely heavily on everything.
Yeah, and so you rely on things like compiler ID whenever the code that produces an asset changes potential output, right? Mm-hmm. So don't you run into issues where people just forget to bump up the compiler IDs?
It has happened every once in a while where someone forgets to bump a compiler ID. We actually don't notice immediately when that happens because we still have the old version of the content, and so either we notice very much immediately or we don't notice for a while because we just didn't rebuild that content. And if they change logic but not the format, then we don't notice. We actually have a split format ID, compiler ID, so if you change how the file's physically structured, there's a different ID to change, and that's incorporated in the compiler ID. In general, that doesn't come up very often. Because the majority of our content is in structured data, we auto-generate what those compiler IDs are. And the engine team's actually very particular. They've gone through a lot because it's painful if they forget. So they've kind of learned to not forget very often. We also use feature branches to do that kind of work. Any local dev builds aren't allowed to upload results. You always have to be in release to help ensure that determinism using SIMD and such. So we have restrictions to help make sure we don't pollute the pool. But because everything's so easy to just regenerate, although time consuming, if there is an issue, we can just purge all those entries from the database. We just do a query and say, no one benefits from this anymore.
Okay, thank you.
Yes.
I think the global repository is your master copy, right, basically?
Sorry, what's that?
Your global repository will be your master copy, the validated, authoritative database.
Yes.
What was the longest amount of time that was down, and if it was more than 4 hours, what was recovery like?
What's the longest time the global service has been down?
Yeah. Yes. And if it was longer than 4, how was 4 work hours, I guess? What was recovering from that level?
We once had a VM controller go down, and then it was down for about 3 hours, although 2 of those were before the standard workday, which just means I get to work more. But for the most part, even that's just contacting IT. Actually, I think one of the longest downtimes we had for that was actually that the time that I mentioned, and this wasn't even a service outage, it was the time that pulling all the content actually exceeded the size of the 4-byte integer. And so literally by using that service, people just crashed. We originally had planned on doing certain queries to delete all those records so that they didn't explode. And at the time, turns out the delete operation wasn't very well indexed. So by time we were able to even execute that query, we had already come up with new code. And I think that actually lasted 6 hours throughout the day as we tried various things that didn't work. In general, because everyone does have stuff already built incrementally locally, it's not that expensive to pull latest content and build even without its assistance. But if you had pulled a branch for the first time, that would have been very expensive. So we just warn people to continue working on your previous build if you can, that kind of stuff.
I see, thank you.
All right, thank you. There will be an overflow, or you can come up and ask questions later if you'd like. Thank you.